We're going to use double integrals to calculate the surface area of a surface. And in order to do that, we're going to think of a surface as a level curve of a 4D function, which is the same idea when we were getting the normal vector to a surface. We were thinking of it getting the gradient of this 4D function, and the gradient of that 4D function was the normal vector to the surface, which we thought of the level curve. Anyway, same idea. But say we've got a surface, z is equal to a function of x and y, and we want to make it as a level curve. So I'm going to move the z over, so it's f of x minus z equals 0, and then I'm going to think of this as the function, and the level curve is where I set the height of the 4D function, the output of the 4D function I set equal to 0. So then this is a surface, but it's also a level curve of a 4D function. And I know that the gradient of that is normal to the surface. So let's get the gradient of that function. Well, we're differentiating the function with respect to x, with respect to y, with respect to z, and the with respect to z is always going to be minus 1. The gradient with respect to x, well, that's just the derivative of this function with respect to x. There's no x's in this minus z. The same deal with the derivative with respect to y. The derivative of this with respect to y is f sub y. That's it, minus 0, I guess. So then here's our gradient vector. And I know that gradient vector points perpendicular, points normal to the surface at any point. So here's it's a picture, I think I just took it from Wikipedia. But the idea that I've got this surface and all these little normal vectors are perpendicular. And what I want to do is add up the area of all these little rectangles, little squares, let's say. And then when I sum up all the areas of those little rectangles, those little squares, then I'll get the area of that surface that's over top of a shadow. So the surface area then, our formula is going to be the sum of the magnitudes of those normal vectors. So the magnitudes of this normal vector is going to be the first component squared plus the second component squared plus the third component squared, square root of that whole deal. This is the magnitude of that normal vector. We want to know the magnitude of that normal vector summed up over little dA, these little rectangles, but really they're shadows, so a little change in x and a little change in y. And we're integrating it over r, where r is the shadow that this surface makes on the xy plane. Now a couple of things. Why should the normal vector have to do with the area? Well, clear. Think of this then. Here's the shadow that the surface makes, and there's its normal vector. If its normal vector, get another one. Here's two different surfaces with the same shadow, which the black has more area, more surface area than the yellow. Why? Well, because it's the black one is tilted more like this. In fact, let's make one that's super tilted. So, I don't know, green. If it's super tilted, it still has the same shadow. It still has the same shadow, but this area here, the length of that is a lot, way more than the yellow. So the more I tilt the gradient, the more area I get per shadow, the same amount of shadow. So it makes sense that it's got the gradient in it. The way that we're taking the gradient, though, this component, the z component, is always the same. So we're scaling gradient sort of as a function of 1, let's say. All right, other reasons why it should be, why this formula makes good sense to us. The gradient of a function points in the direction of greatest increase. If we were increasing the function, this g function, by a little bit, how could we do that? Well, to make it go from this to this, you could just think about painting the outside of the surface. That would be a little change, that would be a little change in the function. So you're talking about the area then. So it's pointing in the direction of greatest area increase, painting that surface. Anyway, let's test this. Let's do an example of this. And we'll test it on something, whose answer we know. So we want to find the surface area of the top half of a sphere with radius capital R. So radius capital R, the equation of a sphere with radius capital R is x squared plus y squared plus z squared equals r squared, so centered at the origin. Here it is here. And I've made, in this case, the radius 1. And I just want the surface area of the top of that sphere. Well, if I look straight down upon it, these squares make shadows. So the region that I'm integrating is over this circle. That's the R region that I'm double integrating over. And these squares near the middle, where the gradient points straight up in the z direction, where the gradient is very much parallel to the vector 0, 0, 1, only pointing in the z direction, those areas are really close to the areas of their shadows. Whereas over here, let's say this blue spot, the gradient points sideways, and it's going to make a small skinny shadow. So the actual area of that blue square is way more than its little skinny shadow, measured by the tilt of the gradient. And when you start to tilt the gradient, instead of pointing straight up, those gradients, because of the way we made it as a level curve, those gradients always have a z component of 1. If we start to tilt it, then it still has a z component of, well, I guess minus 1, the way we built the function. It still has a z component of 1, minus 1 in the z direction, but the x and the y components, when I tilt it, get longer and longer and longer. So tilting makes the vector longer. That's like straight up and down is as short as that gradient can be. That would be all in the x direction. In the z direction. So the area of that little square would be exactly the area of the shadow. Tilt it, and the area of that little square would be more than the area of its shadow. All right. All right. Let's do our. We've got our function. If I want to differentiate this, I need my f sub x and my f sub y. So those will be, we'll write it like that. So there's our f sub x. I need my partial derivatives here. So chain rule, I'm differentiating with respect to x. That r squared minus x squared minus y squared to the half comes down. Subtract 1 from the exponent, so it's minus a half, times the derivative of what's up top, so it'll be the derivative of what's inside, is minus 2x. So that minus 2 and the half cancel. And there's my derivative with respect to x. The derivative with respect to y then, nice and symmetrical, just going to have a y there. And the region, the footprint that we're integrating it over is the circle of radius, the circle in the xy plane of radius r. So let's get our area. We'll plug into this formula then and see what we get. So f of x squared is going to be x squared over the square root's going to get rid of. So let's, when I square that function, I'm getting rid of the square root, and I'm making that positive squared. Likewise, when you do it with the y, okay, there. So now that those pieces are plugged in, dx dy, let's get our radius here. And, okay, I got to go back to, I got to think about what the region, and it's a double integral, x is first. Let's draw this thing. Okay. We're talking about this region here, from R and R. So the top half of that curve, goes curve to curve. X is going from, well, x, we're doing x first. Through the shape, x is starting here and ending here. Starting here and ending here. So I've got the equation x squared plus y squared is equal to r squared. I'm going to solve that for x equals, so x equals plus or minus square root of r squared minus y squared. So this side is the minus square root of r squared minus x squared. And this side is the plus r squared minus y squared. Now we could start at 0 and double it, but let's just, stick with it. Then the y's are going to be lowest y in the shape minus r, highest y in the shape plus r. Okay, so here we're going from minus square root of r squared. Big R squared is the big R squared. That's the radius minus y squared. And then the y's go from minus r to plus r. So now all we got to do is do that integration. With respect to x. Let's common denominator this together. Now let me say first off, if I flip this to polar coordinates, polar integration, because my shape is, the shape of the footprint is round, it's a circle, the math is going to be way easier. So we're doing it with Cartesian. We're not picking the easiest way, but let's see what we get. We'll common denominator this together. If I hit simplify, so the computer made it with minus on the bottom, but minus here. So I'm going to make that multiply and that minus sign through. So there's what I get. Again, if we switch to polar, this would be dead easy. But for some reason, I'm not doing that. We can take this r squared outside as an r. Now that square root is just around the bottom, basically. I'm integrating with respect to x squared. I guess I want to do some trig substitution. That'll turn it into trig anyway. So I'm going to move this. We're integrating with respect to x. So I see something minus x squared. So my substitution is going to be I got 1 minus sine squared theta is equal to cos squared theta. Okay, I'm going to multiply both sides of this by the expression r squared minus y squared, which is a constant. So I'm going to multiply so I can make this a perfect square under the square root sign if I let x equal to the square root of that piece times cos theta. If I do that substitution, then this will be a perfect square, which would mean that dx is equal to, this is a constant with respect to x, times minus sine theta. Oh, my bad here. This is supposed to be cosine sine. Duh. I don't want that minus. I let this equal to sine, and then its derivative is without the minus. Duh. I'm doing trig, so theta d theta. All right, so let's put those pieces in then. Okay, so in for dx, I'm writing this. In for, when I do that substitution, that whole highlighted piece turns into this. Which is what I wanted. I wanted a perfect square under the square root. Now let's see some things cancel, and then I'm going to integrate with respect to, I'm going to change these endpoints in the middle as well, in a second as well. But yeah, let's do that before we do lots of canceling, because everything's going to cancel in a second. When x is equal to this, that's when sine must be equal to 1. And so theta is going to be, now I'm changing everything to thetas. So this must be theta equals 90 degrees, pi over 2. And when this is equal to minus, so that's minus pi over 2. So I'm changing my endpoints as well, which is, then I don't have to change back. Okay, so now let's do some cleanup. This is under the square root sign. It's going to cancel this piece. This is root cos squared, 1 over cos. That's going to cancel that. There's so much canceling, then let's clean this up like this here. Because this all cancels. Nice. because now I'm just integrating the constant r with respect to theta, and that's just r theta. And I still have to go sub in the top minus sub in the bottom. But that'll be r pi over 2 minus r minus pi over 2. Minus a minus is a plus. So this whole thing simplifies to just be r pi. Pi over 2 minus a minus pi over 2. Now I'm going to integrate this with respect to y. There's no y's in there. So it's just going to be r pi y. Sub in the top. That'll be r squared pi minus sub in the bottom, which would be minus, so let's minus a minus, so it's a plus, another one of those r squared pi's. Answer is 2 pi r squared. Area of a circle, okay. Volume of circle, 4/3 pi r cubed. The derivative of that would be area. So the area of a whole circle would be 4 pi r squared. We only did a half a circle, 2 pi r squared. Yeah, it works. Ta-da. And actually, switching to polar would have made this easier, but the trig sub wasn't too bad. So our example, everything worked. So we know how to work this. Let's do another. Let's do one more example. Now we're going to do a plane over a rectangular region. So this is like super general. Because I've got a scalar equation of a plane, ax plus by plus cz equals d. So I've got some tilted plane, and the rectangular region over which we're taking the shadow is just x goes from x0 to x1 and y goes from y0 to y1. So everything's super general. What is the area of a plane with a given rectangular shadow? That's what we're figuring out. So the first thing I need to do then is I need to take this plane and solve it as a z equals, and then I can get it, so that's just move everything over to the other side, divide by c. If c is equal to 0, then it's just flat up and down, and it has an infinite area over a particular shadow because it's perpendicular to that xy plane. So we've already got our answer. If c is equal to 0, it's infinity. So from now on, c isn't equal to 0. I take my two partial derivatives with respect to x, with respect to y, and I'm going to pop them in this formula now. So with respect to x, when I square it, it's just going to be a squared over c squared. And when I square the y, it's going to be b squared over c squared. All right, let's get our, oh, it's a rectangular region, so this is nice. X goes from x0 to x1. Y goes from y0 to y1. So a nice rectangular region. This doesn't look too bad. All right, let's solve. Let's do our, this is the area equals. Now, what do we got here? Oh, this is all, there's no x's or y's in here, so this is just going to be a constant. When I integrate it with respect to x, that's going to be this expression times x from x0 to x1. Which, I'm just working here in the middle, that's going to end up being this expression times x1, this expression times minus this expression times x0. Let's factor that piece out, the square root thing. I think that'll make it, in fact, you know what? This is a constant, right? Since there's no y's in there either, let's just bring that to the outside. So now what do we got? That's going to be integrating x1 minus x0. Which is a constant with respect to y. So let's just do our integration. This is working out not too bad. When I do my integration, it's just this thing times y, and I still have to go sub in the y1 minus sub in the y0, which is going to be y1 minus y0. And we're done. So what do we got here? This, that's just the area of the rectangle. So then this is like a fraction of how much of the area of the shadow. Is it a fraction? It's a number bigger than 1, so I'm not going to say a fraction. It's like a multiple, so that's a better thing. So it's a number bigger than 1. If I multiply the area of the rectangle by this, well, it's the magnitude of the normal vector to the plane, that's giving me how much of a multiple of the area of the shadow we get. But we've got a surface area formula in terms of its rectangular shadow. And if c goes to infinity, what happens when c goes to infinity? When c goes to infinity, then the plane is just flat. D moves it up and down. That means the area of, or the area of the plane over the shadow is the shadow. Sure, that all makes good sense to us now. Anyway, these are two examples of using this double integral formula to get the area of a surface.